Hello friends, now the next topic in operational amplifier is the characteristic of the operational amplifier. You will find a number of characteristics of amplifier given in a textbook, but here we will be discussing only those characteristics which are important from examination point of view. I have summarized those characteristics that is in this list, that is 9 number of characteristics. The first characteristic, input offset bias current, input offset current, then I'll repeat, input bias current, input offset current, input offset voltage, input offset drift voltage, output offset voltage, power supply rejection ratio, common mode rejection ratio, slew rate, and ideal voltage transfer characteristic. Now there are a number of questions based on this particular topic in GATE, in engineering services prelims, and maybe in civil services as well. From examination point of view, this is important, this is important, this is important, then this is important, then this is important, this is important. These 6 characteristics, first 3, 5, 7, 8. All the questions from this topic appear from these, that is input bias current, input offset current, input offset voltage, output offset voltage, common mode rejection ratio, and slew rate. The remaining characteristics are just for sake of coverage. You don't have questions in different exams from these remaining topics. Fine. Now we will discuss these characteristics one by one. Especially you have a number of numericals from in output offset voltage from this, number of numericals from this, number of numericals from this, and theoretical questions from the remaining topics. So let us start. First one, input bias current. First of all, if you remember, let us draw the symbol of operational amplifier. This is the symbol of operational amplifier. This, we have shown this symbol in my previous video. Fine. This is called inverting terminal. This is called non-inverting. This is inverting terminal. This is non-inverting terminal. Say this is positive bias voltage, and this is negative bias voltage, and this is output terminal. This is output. Fine. So we assume that there is a current, that is bias current, entering into this non-inverting terminal. We have another bias current entering into this terminal, that is inverting terminal. Remember, in operational amplifier there is always some current, biasing current, entering into the terminals of the amplifiers. Fine. That biasing current, of course, if you remember the internal stages of the operational amplifier, at input stage we have the dual input balanced output differential amplifier, that is input stage. Second stage is dual input unbalanced output amplifier. Third stage is called level shifter, and fourth stage is called complementary push-pull amplifier. For that you can refer my previous video. And we have gain of this amplifier, that is denoted by A sometimes, or sometimes we write subscript like this, AOL. OL stands for open loop, A stands for gain. So that means AOL is open loop gain of this operational amplifier. So because of the mismatching of the characteristics, there may be different current entering into this terminal and this terminal. These are the biasing currents. Fine. So as far as input bias current is concerned, the input bias current can be different for non-inverting terminal and different for inverting terminal. Fine. So, but as far as single definition of input bias is concerned, we take input bias current IB, which is taken to be the average of biasing current entering at non-inverting terminal and biasing current entering into inverting terminal. This is a small topic, but There can be numerical based on this. There was one numerical in 2018 in engineering services prelims from based on this formula. Fine. So base, that is bias current of operational amplifier, that is input bias current of operational amplifier, is average of two biasing currents entering into inverting and non-inverting terminals of the amplifier. That is known as biasing current. I hope you will remember this formula. This is important. And why there is difference of two currents entering at input terminals? Because of the mismatch of characteristics of BJTs at input stage of the op-amp. Fine. So I hope concept is clear. So this is input bias current. Now let us talk about input offset current. So input offset current is basically the difference of the biasing current entering at non-inverting and inverting terminals of the op-amp. So the input offset current we denote it by like this: input offset current. The input offset current is equal to the magnitude, we don't take sign of it, magnitude of the difference of biasing current entering at positive terminal and biasing current entering at negative terminal. This is called input offset current. And why it is so? Because of the difference in biasing currents entering at inverting and non-inverting terminals of op-amp. If both are same, if both of these currents are same, in that case the difference will be 0. So input offset current will be 0. So input offset current becomes 0 if both transistors have exactly matched characteristics. Fine. But if there is if the characteristics are not matched, then there will be difference of currents or and currents entering at different two terminals. In that case, input offset current will exist, but biasing current will always exist. If the both currents are same, that will be equal to half of the sum of two. So biasing current will always exist in the operational amplifier, but input offset current becomes 0 if the characteristics of BJT or MOSFET at the input stage of op-amp are same. Fine. I hope concept is clear. So try to remember this as well. Again, there was a numerical based on this formula and this formula in engineering services prelims in 2018 based on these two formulas. Now, let us talk about the third characteristic, that is input offset voltage. What is input offset voltage? Remember, if we don't have any input applied to this op-amp, we don't have any input applied, but still there is some output there at the output terminal. So when there is no input applied, we have input. Which input? There is no input signal. I'm talking about maybe AC signal, any of the input, maybe DC or AC input. There is no input applied, still have some output voltage. Why it is so? Because of the mismatching of the characteristics of the operation amplifier. Fine. So or mismatching of the characteristics of the BJTs of the input stage of the amplifier. So because of that, we have some voltage at the output. That voltage is known as output offset voltage. So I am talking about this voltage first. Output offset voltage, that is the voltage at the output terminal of op-amp when there is no input applied. Fine. I hope concept is clear. Now, what is input offset voltage? That is the voltage required to be applied at input terminal, that is nothing but differential input voltage. Remember this, the difference of voltage between non-inverting and inverting terminal. So the input voltage, differential input voltage required to be applied to make this voltage at output to 0. I hope concept is clear. We have seen when there is no input applied, we have some output voltage, that is called output offset voltage. Now the minimum differential voltage applied at the input terminals of op-amp to reduce the output offset voltage to zero, that differential input voltage is called input offset voltage, and we, rather than writing VD, I will be writing VIO, input offset voltage. I hope the concept is clear. Input offset voltage. Fine. So now let us talk about the power supply rejection, that is input offset drift voltage. What is input offset drift voltage? That is the variation in drift voltage of op-amp, that is variation in, I will say, input offset voltage of op-amp per unit temperature. This delta VIO with respect to, or change in input offset voltage per unit change in temperature is called input offset drift voltage, or we can say drift in input offset voltage with respect to change in temperature is called input offset drift voltage. But as far as exam is concerned, you don't have question from this. You don't have question from this topic, but other definitions are important from examination point of view. I hope you will remember this concept. Now we have certain mathematical analysis, mathematical expressions from this topic onward. So we have discussed these 5 topics, right? And there is one more topic, that is power supply rejection ratio. That is also a theoretical topic. I hope you know what is output offset voltage. I hope you know what is output input offset drift voltage, and so on. So up to 5th we have discussed. Now let us talk about power supply rejection ratio. The power supply rejection ratio is again, as far as exam is concerned, you don't have direct questions based on power supply rejection ratio. Rather, you will find no question based on PSSR. Fine, but still, power supply rejection ratio is again the change in input offset voltage. I repeat, power supply rejection ratio is change in input offset voltage per unit change in one of the power supply. Means if I change either this supply or this supply, the change in input offset voltage is called power supply rejection ratio. Fine. So again, I will say you don't have question from this, you don't have question from this. Now whatever we are going to discuss is really important from examination point of view. That is, again I will be talking about output offset voltage. Fine. So let us switch over or switch back to what I discussed earlier. That is nothing but output offset voltage. Output offset voltage of op-amp is function of, that is, input offset voltage and input bias current. First we will talk about input bias current. Fine. We will be discussing two different circuits of op-amp, and then we will find the expression of output offset voltage of operational amplifier. So there are two possible circuits. What are the circuits? First I will be talking about the inverting amplifier. What is that inverting amplifier? In an inverting amplifier, the non-inverting terminal is grounded and we have a closed circuit or closed loop like this. Fine. This is called inverting amplifier. Fine. Or it is also called inverting configuration. There is one more circuit where we apply input at non-inverting terminal, here it was grounded and this is grounded. Fine. So this amplifier is called non-inverting amplifier. Fine. So again we have similar circuit, we have similar parameters, similar resistances, but this configuration is called inverting amplifier. This configuration is called non-inverting amplifier. When you apply input to non-inverting terminal, that is non-inverting amplifier. When you apply input to inverting terminal, that is called inverting amplifier. Fine. In both the cases, the expression of output offset voltage due to input bias current, that is VOO, because of input bias current. Output offset voltage because of input bias current is given by RF into bias current. And you know what is bias current? I have already given you the expression. The bias current is the average of biasing current entering at inverting and non-inverting terminals. Fine. Now the output offset voltage because of input bias current is given by this. This is applicable for this as well as this, for both, for inverting as well as non-inverting amplifiers. Now let us talk about output offset voltage because of the input offset voltage. The expression of output offset voltage because of input offset voltage is given by this, that is output offset voltage, and that is again for both this as well as this, for both circuits, inverting as well as non-inverting amplifiers. This is the expression of output offset voltage because of input offset voltage. Fine. I hope you will remember this expression. This is very important as far as exam is concerned. This is very important as far as exam is concerned. You have a lot of numericals based on this. So I will say this is very important for your exams, competitive exams. Fine. So if you talk about total offset voltage for both circuits, it is applicable for both circuits. So total output offset voltage is the algebraic sum of these two, fine, into VIO plus bias current into RF. But remember, input offset voltage or offset voltage because of the bias current, both can be having same polarity, both may be having different polarities, but maximum possible output offset voltage will be obtained when both have same polarity. So I will say this is the maximum possible offset voltage at the output terminal of op-amp. I repeat, this may be positive, this may be negative, this may be positive, this may be negative, but that will be different. So I'm talking about maximum possible output offset voltage will be obtained when both are additive in nature, both are having same polarity. So this is the algebraic sum as far as the maximum output offset voltage is concerned. So you should remember this. This is again very important for exam. Fine. Now there is interesting part. This part of output offset voltage, or I will say this part of output offset voltage can be minimized. How can we minimize that? Let us see that. This part, that is component of output offset voltage because of the input bias current, can be minimized. How can we minimize? By connecting a resistance called offset minimizing resistance. The output offset voltage because of input bias, I have already shown you that. Fine, this is the bias current. Fine. So the output offset voltage because of input bias current can be minimized by connecting a resistance called offset minimizing resistance, or sometimes it is called compensating resistance. Some textbooks will be saying compensating resistance, some textbooks may be saying offset minimizing resistance. Similarly here, by connecting our resistance in series with non-inverting terminal. So that is offset minimizing resistance or compensating resistance. So this procedure remains same for both inverting as well as non-inverting amplifier. When you connect this amplifier, so this resistance, the value of this resistance, that is very important, that is equal to the parallel combination of R1 and RF, parallel combination of this. So that is R1 into RF divided by R1 plus RF. This is very important. You have many questions in GATE, in engineering services prelims, and maybe in mains as well, based on this formula. So they may be asking what should be the value of this resistance for minimizing the output offset voltage. Fine. So that can be done by using this. When you use this resistance, fine. When you connect this resistance, in that case, what do we have? The output to offset voltage does not become zero. Output to offset voltage is nothing but like this VF, that is into VIO plus, now instead of bias current, I repeat, instead of bias current, now it becomes input offset current. So this is the output offset voltage for this circuit. Fine. But if you don't have resistance here, this expression is nothing but instead of offset voltage, offset current, it is bias current. What is the difference? Basically, bias current is what? Average of these two currents. That is average of biasing current entering at the terminals. And what is input offset voltage current? That is the difference of the biasing current entering at the two terminals. So now definitely this bias current will be less than this, because this is the difference, this is the average. So this is less than this. So when you use in offset minimizing current in the op-amp circuit or inverting amplifier or non-inverting amplifier circuit, the offset voltage will be minimized. But if there is a condition, if the bias current are same for both the terminals, if biasing currents are same, then input offset current becomes zero. In that case, the output offset voltage will be simply because of input offset voltage only. I hope the concept is clear. I repeat, please understand, there can be numerical based on this. If there is no offset minimizing resistance, then total output offset voltage is this, that is bias current into RF. This remains present always. 1. 2. If I connect offset minimizing resistance here, or compensating resistance here, so this becomes input offset current instead of bias current. Please do remember. I hope this concept of compensating resistance is clear. The concept of output offset voltage is clear. Now let us see the example based on the output offset voltage. That is, first example based on this topic is the op-amp used in inverting amplifier shown in figure has an equivalent input offset voltage of 5 millivolt. The output offset voltage is, so we are given simply input offset voltage, nothing is talked about input bias current or input offset current of the circuit. What is the circuit? You can see this is the configuration, and if you remember, we are applying input to the inverting amplifier inverting terminal, and that non-inverting terminal is connected to ground through this resistance. So this must be definitely inverting amplifier. So this is RF, this is R1. So the output offset voltage for this circuit is what? Simply I have shown you the formula. That is, the formula is what? Output offset voltage of the inverting amplifier is given by 1 by RF by R1, or that is 1 plus RF by R1. RF is this, R1 is this, into input offset voltage. So this is given to you. So this is very simple example based on that simple formula. So we could find the output offset voltage. The question was in instrumentation gate 2003. Now again we are given this circuit. Fine. In figure input offset voltage of operation amplifier is 2 millivolt. The output DC error voltage, remember output DC error voltage is nothing but output DC offset voltage. Fine. So again the expression will be similar here. This we are connecting input to the non-inverting as well as inverting terminal. That's fine, but we are given only input offset voltage. So whether it is inverting or non-inverting amplifier, remember the expression of output offset voltage is simple. That is RF this resistance divided by this 1 plus RF by R1 into input offset voltage. So irrespective of the combination, irrespective of the configuration of the amplifier, that is always RF by R1, and RF is resistance connected in feedback path, R1 is this resistance. So we have the output offset voltage given by this expression. Again it's simple. RF is 10R here, R1 is R, so I can find the output offset voltage, and you can see that question was again in instrumentation. Fine. Now let us see this question. This was in electronics 2018. In op-amp based inverting amplifier with gain of 100, you are given gain of the amplifier. The feedback resistance is 47 kilo ohms. The op-amp input offset voltage is 6 millivolt. Input bias current is 500 nanoampere. So we are given input offset voltage, we are given input bias current. The output offset voltage due to input offset voltage and input bias current is given by. Now there is one point given here. We are given feedback resistance, that is RF. We are not given R1, and we are given gain. So remember, in inverting amplifier, the gain of the amplifier is RF by R1. I am just giving you, I am introducing this formula directly, but of course with time you will come to know the expression of gain of the inverting amplifier. Gain of inverting amplifier is given by RF by R1. For the time being, just remember this. So I am given A, I am given RF, so I can find R1. This is A, this is RF. Fine. So R1 is given by this. Fine. Output offset voltage in terms of input offset voltage, we know the expressions. You know R1, you know RF, you know VIO, so I can find output offset voltage because of input offset voltage. Now output offset voltage in terms of input bias current, so you are given RF, you are given IB, so I can find this. So from there I can find the expression of the output offset voltage because of input offset voltage and output offset voltage because of input bias current. So that was so simple. Now let V1 is equal to V2 is equal to 0 and R1 is 20 kilo ohm. Assume that op-amp is ideal except for non-zero input bias current. Fine. What is value of R2 for the output voltage of op-amp to be 0? So here we are given, this is the circuit given to you. So V1 is 0, V2 is 0. Fine. So V1 is 0, V2 is 0, and RF is given to you. R1, this is the circuit, although there should have been the circuit here. So we are not given, but I am introducing that circuit in the question itself. So R1 is 21K. R1 is 21K and RF is basically R1 is given to you. Fine. So we have to find the value of R2, this resistance. So this is the circuit given to you. That was not given in example, but that should have been there. Maybe that may have skipped. But this is the circuit given to you. So to make it output, to reduce output to 0, remember output offset voltage becomes 0 if R2 is 0. Sorry, R2 is parallel combination of RF and R1. I have given, I have introduced that. If R2 is parallel combination of this and this, but these two resistances, if you replace this by equivalent, because that was R1 in the circuit, so this becomes parallel combination of these two. So the parallel combination of these two is what? 10k, 20k in parallel with 20k is 10k. Fine. So parallel combination of 10k with RF. So R equivalent is parallel combination of these two, that is 10k, and R2 has to be parallel combination of this, that is R1, and parallel combination of this. R1 means R equivalent. So R2 must be equal to RF in parallel with R equivalent. So this is the expression. Remember that output offset voltage will be 0 if and only if input bias current is same for both input terminals. That condition I have already introduced. If nothing was given, that means I am assuming the input bias current at this terminal is same as this, only then output offset voltage because of input bias current becomes 0, because nothing was given, and not even input bias current. I will say output offset voltage will be 0 because of input offset current when this is parallel combination of this. Remember, whenever you have compensating resistance here, so output offset voltage is equal to what? RF into input offset current. But input offset current is 0 when input bias current is same for this terminal and this terminal. Nothing has been mentioned here, but I'm saying output offset voltage is 0. That can be only if and only if input bias current for this terminal is same as input bias current for this terminal, that is inverting and non-inverting terminal. Fine. So this has to be parallel combination of these two for reducing the output offset of the circuit to 0. Fine. So these interpretations you have to draw on your own from the given information in the example. So this is all about the numericals based on the output offset voltage. So this topic is important for numerical point of view. There can be numericals based on this particular concept. So this is all about examples based on output offset voltage. Thank you very much for watching the video.